This is Cameron Chai from azonano.com, and I'm speaking to Chris Orzulak, who's an applications engineer for Veeco, and he's going to tell us about their AFM / nanomechanical tester.
This is our Dimension V system. So this is the world's best-selling AFM. Has a large sample area for doing. You can do large samples, small samples with this. Very high resolution. It has closed-loop control X, Y, and Z. And so that gives you the abilities to not have any drift or creep in your measurements as you're going along. So this is again the best-selling instrument that we have, just because of the access to the sample. So we can look in here a little bit. We could see. So this is the actual head where the AFM is. So this part here is the AFM. The rest of everything here is just staging to get your parts down to get your tip down to the sample in the AFM. So actually here, can't see it now, it's hidden under the head, but that's where the sample is sitting, that we're scanning something right now. And this system is run off our Nanoscope 5 controller, so it's our latest and greatest controller. It came out about 1.5 years ago. And that, when it first came out, we didn't really have many applications for it, but one of the things we've just come out with is this harmonics imaging. So what that is a nanomechanical measuring system. So not only do we get topography, we could also get nanomechanical measurements as we're doing it. So we can get things like stiffness, adhesion, and energy dissipation between the tip and sample of the part that you're measuring. So come over here toward the software. So again, that Nanoscope 5 that allows us, to do these high-speed data acquisition things. We can capture up to 50 megahertz speed, so we can get true nano time scale measurements and a nano vertical scale kind of measurement. So what we're doing here, so this can give us several different things. And so we have 8 channels of data here. One is our height. So this is just the standard height measurement that we can get with any AFM. But what we add in here is the ability to get other things, like the amount of force we're actually applying to the surface. So we can see this is a blend of 2 different polymers. This is a polystyrene and a low-density polyethylene. So we could see that we have more force on the polystyrene and less force on the polyethylene. And we could also pull out information like stiffness. So we get this channel up. So we're actually getting stiffness in a real Young's modulus, a real nanoscale modulus measurement. And the way we're doing that is we're capturing with each tap. So you can see what this plot is a plot of the force versus the time. So as each individual tapping cycle, this cantilever is tapping at about 30 kilohertz. So this section here, which is about 10 microseconds, is where the tip and sample are actually interacting. So you can see here there's no interaction. This is where the tip is hitting the surface, and we see how much force is being exerted by the tip onto the surface. So we have about 4 nanonewtons of force, and we're getting this information at each pixel. So from that information, we could build what we call a force curve. So the force curve is this then showing our force versus separation. So from this information, we could build, using some mathematical models, we could build these maps over here, where we have the adhesion map, the stiffness map, and then energy dissipation, and also peak force. We could really see that one's really showing up nice here. We could see the peak force. So this is our newest thing. It works mostly right now in the polymer ranges. It's goes from about 10 megapascal to about 10 gigapascal range of modulus numbers we could detect with this. And that's our latest thing, but this is something that was enabled with that Nanoscope 5 controller, with the high-speed data acquisition and the all-digital control, using the FPGA and that thing, so we could program it to do these types of different measurements. If there's anything else we can do. What else? And actually here we didn't talk at all about this, but this is the actual tip, and what's different about these harmonics tips. The probe is the tip is offset. In a typical AFM, the actual tip is underneath this cantilever, would be in the center, but on these probes it's off to the side. So when this is off to the side, it creates a torsional motion, and that's what gives us the ability to collect these force curves at each pixel by that torsional motion of the cantilever.
All right, Chris, thanks very much for your explanation. And we hope the machine continues to be a good seller for you.
Yeah, thank you.